it's the radius of base of the cylinder. Okay, that's an important thing that we should keep in our head. And let's write the formula. So what are we gonna do? We're gonna do the same that we did, with the sphere. Okay. We're gonna make some fancy triangles. Maybe a triangle here. Okay. And then write the formulas. Okay. So let's draw this triangle. Okay. So let me draw this triangle. So this is really the base of it, the base of the triangle. So 1, 2, and 3. So if I'm drawing the triangle with angle theta, and these sides are 1, 2, 3. So 1, 2, 3 are going to be where?
So 1, 2 will be the perpendicular.
So the 1 would be this.
This.
Okay.
Then 2 will be.
2 would be hypotenuse or?
Perpendicular.
Are you sure?
Yes, sir.
2 would be the perpendicular, 3 would be the hypotenuse section. Okay. Now this distance in rectangular coordinates is what? X. So if you want to find, for example, x, you need to find really the, what do you call, the hypotenuse of it. What would be this distance?
X.
ये क्या हो? देखा ना? ये distance तो ये distance क्या है? Okay. I mean, if you for example see from the rectangular coordinates point of view, this is r.
Yes, sir.
Okay. This distance is r. ये distance r है hypotenuse.
Yes.
So this distance is r. So if this distance is r, what should be this?
R cos theta.
So this would be the r cos theta. That's it.
Yes.
How about this one?
R sin theta.
Paki baat hai.
Yes, sir.
This is going to be r sin theta. ठीक हो गया? अच्छा. अब अगर इस triangle की तरफ आएं, so let's think about this triangle. ठीक है. So
4, 5 comes.
ठीक है. So okay. So okay. If you are comparing it with the rectangular coordinates, aren't we done? Because we really don't need to consider this actually, because so we don't have an angle here. We're just saying that okay, this is really the height is z. Okay, so what is x now? If you compare this picture with this picture, so x is really the base of this triangle. And what is the base of the triangle? It's r cos theta. So what is y here? So if you compare that y with this y, so it's this distance, but how much is this distance? Let's say r sin theta. Okay? And how about z? The z is same as z. Okay? You don't have to. So the x square plus y square, this z is going to be the z actually. Okay? Because, in both cases, this is really the same line actually. Take it? Are you getting the point?
Yes.
The same point. So these are the what we call cylindrical polar coordinates if you wish. So the same question, if you have r theta z and you want to have this r cos theta and r cos theta and r sin theta and z, and you want to make it diffeomorphism. So the first thing would be calculate the Jacobian. Okay, determinant of the Jacobian, and you can calculate the Jacobian of this phi, and it turns out to be only r.
So just the second thing.
Yeah. So what does this mean? So is there some thing that can turn r to, what do you call? Okay. So is there something that can make Jacobian 0?
That's radius 0.
Yes, so you can't take r to be 0. And that's the reason you can't take r to be 0 as well actually. In spherical coordinates में वहाँ पर भी r पर depend कर रहा है Jacobian, so you can't take r to be 0 as well. ठीक है? So Jacobian, if you take r to be positive, you are safe, you are okay. Okay? How about theta?
Jacob does not depend on it.
Then Jacobian नहीं करता, but
Diffeomorphism.
so the diffeomorphism होने के लिए the second condition that you need, that should be your bijection relation. So what should I do with that? We need to restrict the theta actually, because if you keep on moving along, this length at a point will come when it's gonna repeat the value actually. So your theta should be where?
Between 0 to 2 pi.
So what should be the domain actually? You can say the domain is 0 to infinity for radius, 0 to 2 pi for theta, and what should be for the z? Z could be anything. Z could be anything. Okay, so it should be R. Does it make sense? So if you choose this domain, then this guy is immediate if you want it. ठीक है? This guy is immediate if you want it. That takes you from one coordinate to another set of coordinates actually. Okay. Question. How the volume would be related in this case? So the dV I know in rectangular coordinates is dx, dy and dz. And how it will be related with, for example, cylindrical coordinates is going to be dr, d theta, dz, but you need to multiply with r. Okay. So you have a diffeomorphism that takes, for example, a smaller chunk of, for example, cubical volume, and it turns into a cylindrical volume actually. And how they are related with each other. So R is the factor that is compensating for the volume. Is it making sense? The same, what do you call it, ideas just taken into the 3-dimension when you are. So transitioning from 3-dimension actually to 2-dimension to 3-dimension actually. Is it making sense? That's it. And once you have this, I can state the change in variable formula. So let's just state the change in variable formula. Let's do one example of it. Change in variable formula for triple volume. So here's a careful statement of it. So you're going to say, suppose you have some subset of R2, okay? R3, sorry, so some part of R3 that is rectifiable and open it. Doesn't reach the bound. Okay, so it's a rectifiable open volume. What was the meaning of rectifiable volume? You can put it in a box actually. You can put it in a box. You compare its volume with volume of some box. Okay. So rectifiable open, and let F is a scalar field associated with it. So on this volume you are defining a scalar field F from A to what do you call it? R, be a bounded continuous map. Continuous function So imagine you have a diffeomorphism that takes you from another volume B into this volume A. Okay. And this is a diffeomorphism. Then the volume integral of f, okay, over A is equal to what? This is equal to the volume integral of f over B composed with phi, okay, and multiplied with what do we call the Jacobian actually determinant of J phi. Is it making sense? And if you write this expression more explicitly in classical notation, okay, then it's going to look like this. In classical notation, it's going to look like this, that I have triple integral of f of x, y, z evaluated over A with respect to say dx, dy, and dz. Okay. And what? And this should be equal to the triple integral of over B of f of x, but the x now is depending on
R phi.
no, r phi theta nahi. Like r phi theta is one example, r theta z is one example. So you're going to have a generic transformation. So u, v, and w. Y also u, v, and w. Z also u, v, and w. Okay. Times the Jacobian of x, y, z. Determinant of the Jacobian of x, y, z with respect to u, v, w. Okay. Times du, dv, and dw. That really is the variable phi. What does this expression mean? You have this volume, and in this volume you want to look at it, this f, you want to quantify this effect. So how much of f lies in this volume actually? And then you want to sum up all this f over the entire volume V. So you have this volume V and this f is something in the volume V actually. And then now you are changing your container actually. So previously you have a container, okay, that was a cube, and you were taking an object into that container, okay, that object is f, so f is, so think about it. So like, think about the sugar in a box actually, or some grains in a box actually, taken, in some volume, taken, you have some funny volume, and in that you have, a lot of sugar. And then you are taking a container, okay, that is rectangle, and just filling it with that container actually, okay. And then you are saying that, so I mean, if you see practically, you may, you may say that, for example, before taking through the container, you may say that in the space, every point in the space of that container which contains the sugar, every point has a sugar piece associated with it actually. So that's really like a scalar field actually. So every point of the container has an associate. समझ आ रही है बात?
Yes,
Okay. So think about it. कोई बोरी समझ लें, कोई कुछ just shopping bag समझ लें in which you have what you call sugar actually. So I can say that in that volume of shopping bag or bori or whatever, ठीक है, every point associates a sugar piece or what you call piece of a sugar actually, okay, grain of a sugar, little piece of a sugar. And then you are taking a small container like dx dy dz. Then you think how much of sugar can be fit into this small container actually. Okay. Then the change of variable formula is really changing the container. That's it. So instead of taking, for example, a cubical, container through which you want to take, for example, sugar, now I think let's take a cylindrical container and take the same actually. And then you are saying that, how much these two containers are related with each other actually. Okay, the quantity of the sugar that you can put in cubical container is related with the quantity of the, what you call sugar that is, you take in the cylindrical container actually. Actually, you're doing the same thing, okay, with the two different containers, okay. So the diffeomorphism is telling you that how much the quantities are related with each other. That's essentially what it is doing. That, okay, you take this container and you want to see how much of F is in this container, and then you want to sum that all up, and it's going to give you that how much total you have actually. Kile ke kitne hain bhai? Doodh malum karna hai. You don't know the quantity of sugar actually. You don't know the quantity of the milk. Then you're going to take a container whose, what do you call, volume, you're just going to fill it and you're going to see, okay, 1 liter and 2 liter and 3 liter, oh, it's 3.5 liters actually, with this container, okay. But if you have a container that can measure things in kilograms actually, so you're going to say that, okay, you have 1 kilogram and 2 kilogram and 2.7 kilogram actually, because, liters and kilograms are different sizes, okay. So that's what essentially you're doing. So dx, dy, dz is same. So now you're saying they're changing the container. So you want to now taking the du, dv, dw. Okay, that's a new container actually in which you want to see the F. But since you want to have an equality, so you need to know that, okay, how this container is related with this container actually. Okay, so the Jacobian is giving you really the relationship between the volumes between the two containers actually. So yeah, this is what is essentially happening. Okay. So let me formulate one problem and then just pose its solution. I'm not going to solve it, you have to do it for yourself. And then move on to the new topic, and the topic would be divergence theorem. So let's do one example. So the example is this. You have a hemisphere, in other words you have a slice of a sphere, so it's like an upper sphere or a lower hemisphere. So you take a sphere and slice it from the middle. Okay? So you're going to get two pieces of the spheres. They're going to be half spheres, like a semi-sphere. So that's really the hemisphere. Like you slice the circle into two parts, and we're going to call it a semicircle. So you have this hemisphere, and you want to know, where does really, the centroid of the hemisphere lies actually. Where is really the middle of it actually? I mean, where is the center of mass of it actually? Okay, where is the center of mass of it? So here's an example, and it says that compute the centroid, okay, of hemisphere. Okay, solid hemisphere. So I have this sphere, and I'm taking this upper part of it, this part actually. This part. Okay. Only this part, I'm ignoring the other part. Okay. Alright, so what would be the equation of it? So how you can represent this entire, this a solid hemisphere. So you are also interested in the inner parts of it. Okay. So what would be the expression that can represent everything, every point inside this hemisphere?
in Cartesian coordinate system,
Yes, Cartesian.
R is equal to square root of x square plus y square plus z square.
नहीं, ऐसा नहीं है. So you're gonna have x square plus y square plus z square. Okay. For example, if you say that this radius is a, if you're gonna take equal to a square, then you're only talking about the upper layer of it. You're talking about the surface of it. Actually.
Less than equal.
Okay. So you need to have
Less than equal.
less than equal. And if you are, for example, placing your hemisphere, in three-dimensional manner, for example, in three-dimensional system in this manner, okay, then you are only interested in the upper part of it. In other words, you are only interested in the, interested in that part when z is bigger than or equal to 0. Okay. Not interested in the lower part of the z. Just interested in the z. So if I don't put this restriction, then you are talking about a solid sphere actually. That's really a solid sphere. So the sphere with all points, on it and in it actually. So I'm just interested. So this is telling you that okay, you have just really taken. Does it make sense? But this doesn't matter. You can place this in this manner. Okay, so I can place this, for example, this solid sphere in this manner, and then I can say that okay, I have this x square plus y square equal to z square less than or equal to a square, but I'm going to say that y is greater than or equal to 0. Okay, and then everything would be the same. Okay, so it's just this, and this is an important point to realize. The reality, reality is this point in this space. Reality is this, for example, point in this space. This x-axis, y-axis, z-axis, and r, theta, phi, spherical coordinates, or this or that coordinate, is just fiction that exists in our head actually. Okay? It's just a way to make sense of it. Because when you want to measure the things, you want to measure through some reference actually. Okay? So how do you measure, for example, the weight of some quantity?
So we have reference weight.
So you have the reference weights. But how do you know that this reference weight is really?
So in Geneva concept they.
So you agreed upon weight actually. So it's just defined. So kilogram doesn't have any definition. So you say that okay, this much number of particles when you put together is gonna be a kilogram actually. Okay. But is this weight really a kilogram? This is just our understanding that it's a kilogram weight. Huh? So all these things are, really the tools to make sense of things. They are useful tools. They are very useful tools. So I'm saying that when I have a hemisphere, when I place it this manner or some other manner is not going to change the calculations actually. Okay? They're just placing it in one manner and then, trying to make sense of it. Okay? Okay. So if you want to find really the center of mass of it, so what you need to find 3 coordinates. Okay. Centroid of it, the x bar and y bar and z bar. So someone remembers what was the formula? You had similar kind of a problem when you were, जो कि नहीं हुआ था है.
1 over m.
1 over m. Okay. What should be on the place of 1 over m here? Okay. So you're going to calculate the volume. So you're going to have a volume. I'm going to say you have a volume of. So take the volume of V. But volume of what? So you need to integrate something. Integrate what? So take this scalar field x. Okay. And integrate dx, dy, and dz over. ये the volume है. Is it making sense?
Yes.
And similarly, you can have y bar, that is going to be the 1 over volume of V, the entire volume, okay, times this volume actually, okay, that lives under this plane X actually, okay. And similarly you can have a formula for Z actually. Question. One of the trouble with evaluating this integral is going to be, so what would be the trouble when you can evaluate this integral? Okay. You need to find the limits on x, y, z. Okay. Everything is easy. If you can find limit on x, y, z, you are okay. So the question is, how can I find the limit in x, y, z? But if I wish I can, try to find it. For example, z goes from 0 to up to what? Up to a. Okay. The height and radius of it. But if you have an arbitrary z, and okay, so how about x and y?
Y 0 to pi.
So in other words, even if you write the limits, it would be complicated limits actually. Okay. So if it is a sphere, why not to use the spherical coordinates to turn it into what you call? Is it making sense? So what would be, the description of it in spherical coordinates, spherical polar coordinates. So what you need to do, you need to turn this into spherical polar coordinates. So when you're going to do it, what you need to do? You need to have another region, okay, or maybe V star say. You're going to have r theta phi, but what should be the restrictions on r theta phi actually? What should be the restriction on r theta phi? That can represent every single point in this region actually. So r can be anything
about 0.
0 to a, above 0 to a, because you can't go beyond a. You don't have to, you don't need to go beyond a, because then you will be outside of the limit here. And how about theta?
It can be from 0 to 2 pi.
So 0 to 2 pi.
But we can include one
nothing
point.
wrong in it.
We can include 1 point.
फिर ये है कि उसमें वो देखना पड़ेगा
जो को भी उसका.
जैकोबियन वाला के, उस पर कोई फर्क नहीं पड़ रहा. And how about phi?
So वो
It's not going to be now pi by 2 to pi by 2, because then it's going to be the entire sphere. So
0 to pi. Pi by 2. No.
0 to
2 pi.
pi by 2. So this is really.
0 to
Okay. So in other words, if you are moving on any point on this hemisphere, you don't have to go beyond the pi by 2. You always, can reach to this point by moving some angle that is less than pi by 2. So you pull out, you go along, the hemisphere, and then you move some angle with 0 to pi by 2. So 0 to pi by 2 would be enough actually. Okay? And then you say what? So the x bar is going to be now this 1 over volume of V, the triple integral. X turns out to be what in spherical coordinates? So it's going to be R. Okay? So you're going to say it's going to be what? R cos theta cos phi, and dx dy dz is going to be, Jacobian is going to be r square sin phi. Sin phi or cos phi? Cos phi. R square cos phi and dr d theta and d phi. And I know the limits on r, so it's 0 to a, so on theta it's 0 to 2 pi, on the phi it's 0 to pi. That's it, and solve this integral. Now it's easy to solve that. Just think about it. It's simple sines and cosines. And first we're going to integrate with respect to r, Okay, keep everything as it is and then put limits and then integrate, for example, with respect to theta, which is simply cos theta. Okay, and then integrate with respect to phi, which is going to be cos square phi.
सर
Okay.
ये सवाल है सर, ये जो फाई
एक
है
चीज
सर,
है, हाँ?
ये जो फाई है सर, हम इसको पाई बाई 2 तक कर रहे हैं, लेकिन अगर हम हेमिस्फीयर ले रहे हैं तो हो सकता है कि 0 से फिर कर पाई तक भी तो आ सकता है ना सर। ऊपर जो स्फीयर है हमारा, हम नीचे वाले पोर्शन को अगर यूज़ नहीं करें लेकिन फिर भी पाई तक तो आ सकती है ना, ये